Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 21 of this course on machine learning for earth system science. So today we will be talking about spatio-temporal modeling of extremes. So we are still in module 3 where we are like exploring different applications of machine learning for discovering new insights in earth systems. So the concepts which we are going to cover in this lecture are Markov switching process for weather conditions, spatio-temporal modeling for extreme value distributions, and validation of extreme event simulations. So like so these the most of these concepts we have studied in isolation in module 1. In this lecture we will see some concrete uses of this, or we'll come across some research papers where these concepts have been used for for various applications in the in earth sciences. So the first topic which we'll talk about today is the modeling of heat waves. So we know a heat wave is is a phenomena where the temperature is high for in a region for several days at a stretch, and when I say it remains high, it means above some particular threshold. Now these thresholds they can be either absolute and fixed, that is same for all locations, or it can be location specific, that is for some locations 40 degrees Celsius might be the threshold, for some other locations 32 degrees Celsius might be the threshold, and so on, depending on whether it's, let's say, it's a hilly region or not. I mean, what is the standard in that region. Now these thresholds, they should be flexible and they may vary spatially also. What I mean by the thresholds should be flexible, I will come to that in a bit when we see a clear example. Also it need not be only about maximum temperature, humidity is also found to play an important role during heat waves. That is, the higher is the humidity, the more intolerable a heat wave becomes and results in a higher mortality. Earth scientists in recent times, they are also considering humidity as a possible factor while defining the heat waves. So the approach here which we will discuss is to consider the weather state as a Markovian latent variable, or ST. So this is a latent variable because weather state by itself is not an observable variable. It's not something that can be measured directly. It is just a conceptual quantity which is it takes two value, 1 or 0. If it is 1, it means that a heat wave is on, and if it is 0, it means that there is no heat wave. And then there is the observation YT, which depends on the observation of YT, that is the daily maximum temperature, which depends on ST, that is the current weather state, as well as on YT minus 1, that is the maximum temperature on the previous day. The second, it depends on the second thing on YT minus 1, because like the maximum temperature is unlikely to change very drastically from one day to another, even if even if there is a heat wave or not. So this is the it is real the Markovian dynamics, that is that is in this paper, that is which we are going to discuss. The Markovian dynamics is inserted on this ST variable, but the YT is also considered as a random variable which is conditionally dependent on ST. So let us see how they model the whole thing. The heat waves merit careful study because they inflict severe economic and societal damage. We use an intuitive and informal working definition of a heat wave, a persistent event in the tail of the temperature distribution, to motivate an interpretable latent state extreme event model. A latent variable with dependence in time indicates membership in the heat wave state. That is to say, if ST is equal to 1, then we will say that it is a part of a heat wave and otherwise not. The strength of the temporal dependence of the latent variable controls the frequency and the persistence of the heat waves. By persistence, I mean the for how many days at a stretch it remains active. Within each heat wave, temperatures are modeled using extreme value distributions with extremal dependence across time accomplished through an extreme value Markov model. One important virtue of interpretability is that model parameters directly translate into quantities of interest for risk management, so that questions like whether heat waves are becoming longer, more severe or more frequent are easily answered by querying an appropriate fitted model. We demonstrate the latent state model on two recent calamities, example the European heat wave in 2003 and the Russian heat wave in 2010. So, before going into the model, let us take a look at the data. So, like this is the maximum temperature in JJA, means June, July, August, the daily maximum temperature at Paris and Moscow. So, here basically this is to study the relation between yt and yt minus 1, that is like we earlier mentioned here that the observation yt depends on st and yt minus 1, that is the previous day's maximum temperature. So, here we see, like as you can understand, that we see a very linear relation between yt and yt minus 1. That means that that is on any given day the maximum temperature is roughly the same as the previous day's maximum temperature. That is why we cannot consider yt and yt minus 1 as independent. We must consider some kind of a relation between yt and yt minus 1 whenever we are developing a model. That independence is that relation has to be strong enough than what can be captured if we do it like a hidden Markov model where yt depends only on st. So this kind of linear relation between yt and yt minus 1 we see in case of both Paris and Moscow. And now, like these are the two use cases of the heat waves which they have considered. Now, the interesting thing to for these heat waves might be that see, this is the heat wave and this is like one heat wave, this is the other heat wave. So, as you can see, if we set some kind of a threshold, like it may not look like a single heat wave. So, like even during this event, there are not all the days you can see are equally hot. There are some days there is a period of 3 days where the temperature has actually slightly dropped, but it may, so if we define something like a threshold, it might end up, some of the intermediate days may end up dropping below the threshold, but that does not mean that these days are not part of the heat wave. They still are, even if the temperature might have temporarily dipped a little bit. A similar effect is seen in this case also. In fact, here it is even more prominent. Like if you see, like these few days, they are also having quite a like similar temperature as this heat wave period, but they are not. They are not necessarily going to be considered as a heat wave. So, now if we consider the Markov switching process which they have considered, so these are the latent state variable which indicates the presence or absence of the heat wave, and we see the corresponding observations of the daily maximum temperature. So, the Markov, we are calling it as a Markov process because ST is or ST or YT for that matter, both are going to depend on only the previous observation, not on anything further. So, like we can say that ST is independent of ST minus 1, ST minus 2, etc. based on ST minus 1. That is, if we know ST minus 1, then that is enough to or that itself carries enough information about ST. Considering past values, we will not add anything. Now, also note the difference between this model and hidden Markov model which we had discussed earlier. So, in case of hidden Markov model, there is no relation between the observations. Yt is just depending on St. Yt minus 1 depends just on St minus 1 and so on. It's that does not mean that in a hidden Markov model Yt minus 1 and Yt are independent. there is dependence, but that is through the S's. But in this case the relation between yt and yt minus 1, that is quite strong, and such a relation is unlikely to be captured through like indirectly through the S's. That too especially when S is binary. If S was itself a real valued variable, then it may have still been possible to capture, but given that S is a it is a binary variable which simply takes two values, 1 or 0, that means the variance of the emissions in each case is will be quite large, and it will not be able to reflect the relation between yt and yt minus 1 that we observe. So the extreme value distribution is used for this yt because these, as you may remember, these are the daily maximum temperature. So like in an earlier lecture in module 1 where we talked about extreme value statistics, we talked about extreme in two senses. One is the block maxima and another was the peak over threshold. In case of peak over threshold, we are talking about that is about percentiles and so on, but in case of block maxima, we are like there is a set of observations out of which we are considering the maximum values. So in this case also, since we are talking about daily maximum temperature, now in a day there are we have many observations of temperature, maybe hourly and so on. Even if it is hourly, there are 24 observations. If it is per minute, then we have like many more observations, and that is we have 1440 observations per day, etc., etc. So like in each case that is we are talking about the maximum temperature, so we have taking the maximum over a set of values. So that is why in this case we should go for the block maxima approach, and we have also discussed earlier that the block maxima that follows what is known as the GeV distribution. So like also the GeV distribution, so in case of GeV distribution, that like this is how it is defined, that given that y is high enough, then the probability that y is above a threshold above some particular value y, it follows this kind of a distribution. So like where we have this like we have the different parameters like epsilon, sigma, etc. So this is the emission distribution. And then we so when we are talking about yt, okay, so first of all, how does this whole thing factorize? That is that is we have the time series of the y variables as well as the sequence of the s variables. So now if I want to like express the sequence of observations y as a function of the sequence of states s, then this is how the whole thing factorizes. So both y and s are random variables, but assuming that s is known, this is how the distribution of y it factorizes. That is yt is basically it's like it has to depend on yt minus 1, st as well as st minus 1, and so now we can say that in different situations we will have different distributions on y. So suppose there is no heat wave, in that if it is not a heat wave, then the daily maximum temperature can simply be considered to be a Gaussian distribution. Why? Because like if there is no heat wave, then we may not be able to say this kind of a situation that y is above above some variable u, that is that kind of threshold thing may not be there in this case, but in like if the but in case there is no heat wave, we may just consider it to be Gaussian distributed variable, which of course includes yt minus 1 and so on, and mu is a like the parameter of the Gaussian distribution, sigma is the variance parameter of the Gaussian distribution, and so on. Now during the heat wave conditions, again, that is the distribution of yt given its yt minus 1, st minus 1 and st. So st minus 1 equal to 1 and st equal to 1 means that it is that t is the day t is inside a heat wave, that is a heat wave has already started. In that case, like we can express it as this kind of a joint distribution. So we will see how to parameterize these kinds of joint distributions, and apart from that, there are these transition periods where either st is equal to 1 or st minus 1 equal to 0, means a heat wave is just starting at time t, or the reverse. Sorry, this is a typo, it will be 0 and 1, which indicates that the heat wave is ending. So in that case, we use a surrogate variable called u, or rather, sorry, not surrogate, you can call it as a link variable called u. So when Sj is equal to 0, that is the heat wave has not yet started or has ended, we will still use the something like the Gaussian distribution for the observation, and once the heat wave has started or has not yet ended, we will use the other distribution for for the observation. So this u, this is transformed to that is by this inverse logarithmic transition, and then there these kinds of mathematical transformations are carried out. So these basically ensure that the variables, I mean the observation variables, they follow the distributions which they are supposed to follow. I mean these kinds of marginal distributions, they follow the marginal distributions which we have considered in the both the heat wave situation and the non heat wave situation, and this is what the joint distribution looks like. So finally what happens is that, so we have all these parameters, so we need to estimate the values of the different parameters. For the non heat wave conditions, we have the mu and sigma parameters of the Gaussian distribution. For the heat wave situation, we have these sigma and epsilon, these xi parameters. So all these parameters need to be estimated. So what they do is they have observations, so they use some variable, some parameter estimation techniques such as the EM algorithm, the expectation maximization, and by which they which enables them to estimate the parameters in the presence of the latent variables s. And once they have done it, then they are able to estimate the probabilities at the different time points. And so as you can see, these color coding, this red color, this indicates the probability of having a heat wave on the different days. And as you can see, in these days in the middle, where the temperature has actually dropped to normal levels or to near normal levels, even though they are within the heat waves, as you can see, they are still shown to be to have high probability as being part of the heat wave. Why is that the case? That's because we are still considering the previous day's temperature yt minus 1, and because in the previous day the heat wave was still active. So although on this particular day the temperature may have fallen, because of the previous day's influence, we are still assuming that is, we can still guess that the heat wave is still active, it has not ended yet. So and similarly, then if you consider these days, it's possible that they are also part of a heat wave, but with a much lower probability. Similar thing we see in the Paris heat wave also. And then once we have that is, once we apply this technique to identify the heat waves, we can also study the different properties of the heat wave and compare them with what is actually observed. So here they have with the different properties of the heat waves, they have considered the durations of the heat waves. So in different locations, a heat wave may typically have different durations. Some locations may have short heat waves, some other locations may have long heat waves. So they have studied that the distribution of duration in different locations, according to their model, as well as according to, and they can compare the results obtained from the model to what is actually observed. Then apart from that, other parameters are number of heat waves, that maximum temperature during the heat waves, and so on and so forth. Now apart from heat waves, so this extreme value modeling, this can also be used for extreme rainfall modeling. So, the GEV distribution which we talked about is like for the block maxima case, the GEV distribution may be used for modeling the monthly or annual extreme values, and these the GEV distribution parameters, if you remember the GEV distribution, it has like 3 parameters, the shape, scale and location, and these parameters they may vary smoothly over space. So, the parameters can be, if we, so let us say we have observations at some locations which might be some isolated locations, may be different cities of a country and so on. In the intermediate places we may not have observations. So, from whatever places where we do have observations, let us say in the 4 cities, then in each of those 4 cities we can estimate the parameters independently and then use some kind of interpolation to estimate the parameters at the other at any arbitrary location in that region, under the assumption that the parameters vary smoothly over space. An alternative approach is to define some kind of a spatial prior distribution, and that is instead of measuring them independently at the different locations, let us say that there is a prior distribution, something like a Gaussian process, and the parameters at all locations, including those locations where observations are available, these parameters are actually drawn from that kind of a that spatial distribution only. And then this approach allows us to estimate extreme event return periods and return levels at all locations, even at those locations where there are no observations. That is, at any given time I may not know whether an extreme event is happening there or not, because I cannot observe, but in a statistical sense I can know how extreme an extreme event is likely to be there. That is, like when we talk about return level, I am just asking, I am basically asking like how much is a 100-year flood or how much is a 100-year heat wave in that location. That is, say for or if I may frame it in a differently, that is what is the 99th percentile flood, or what is the 99th percentile heat wave that might happen in any given location. So, the first approach which we talked about, that is measuring the GEV parameters independently and then using spatial interpolation, was used in this particular paper. So this is by Professor Daniel Cooley. He is one of the most active researchers on this spatio-temporal extreme events. So, here they use these GEV distributions in a particular region, and they actually carried out the parameter estimations of the GEV distributions and then used something like interpolation to for all the other regions also where they do not have observations. So, this is what the model fit looked like, where they that is they are so if you remember the QQ plots which we discussed when we are talking about extreme, so this is something like that. So, like here they are basically comparing the QQ plots of the observations as well as the models, and so ideally the QQ plot should go like this according to this red line. So, in different models which we are seeing that in some cases the model slightly underestimates the observed extremes, and in a different model it may slightly overestimate the so if we consider some kind of an ensemble of these models, we are more likely to get closer to what is observed. So, this is what their interpolation may look like. So, here you can see some plus signs. So, those are they are the different cities like Fort Collins, Boulders, etc. So, these are all cities in the Colorado state of US. So, at these locations they have sensing facilities where they can actually measure the amount of rainfall. In other places they may not be able to measure it, but they are still estimating it because they have by using the approach of interpolation. And also when they are doing it, they have to take into account other covariates. That is, when they are estimating the parameters at other locations also, like as you can see, so there are these red regions and the blue regions. So these blue regions are like on the mountains, that is they are at a higher altitude. So at these higher altitude the extreme rainfall parameters can be somewhat different because the altitude itself plays a role. So they actually like take that altitude as a factor when they are estimating the different spatial parameters. So and now another paper on this same topic. So as I said earlier, rather than estimating the parameters independently at the different locations, we can also do it by considering the parameters to be part of some kind of a prior spatial distribution. So that is what is done in this paper. So here what they are saying is spatial climate data are often presented as summaries of aerial regions such as grid cells, either because they are the output of numerical climate models or to facilitate comparison with numerical model the climate model output. That is, when we some kind of a process model is run, it is usually run on a grid structure. That is, there are no point wise observations, but actual observations are always point wise, they are never gridded. So now these gridded observations, they are basically summaries, you can say, over a particular region. So we may have several measurements in a region, and the gridded representation is something like the mean of those observations and so on. Now extreme value analysis can benefit greatly from spatial methods that borrow information across regions. For Gaussian outcomes, a host of methods that respect the aerial nature of the data are available, including conditional and simultaneous autoregressive models. However, to our knowledge, there is no such method in the spatial extreme value analysis literature. In this article, we propose a new method for aerial extremes that accounts for spatial dependence using latent clustering of neighboring region. By aerial extremes, what they mean is like the spatial block maxima. Earlier, when we talked about block maxima earlier, we are talking about temporal block maxima. Now here it's this is talking more about spatial block maxima. That is, we have observations at different points, and then and they may have their individual maxima. But how about the summary maxima of the entire aerial region, which we need for the gridded representation? We show that the proposed model has desirable asymptotic dependence properties and leads to relatively simple computation. Applying the proposed method to North American climate data reveals several local and continental scale changes in the distribution of precipitation and temperature extremes over time. So these are the different variables which they have considered: the annual maximum temperature, annual minimum temperature, the annual maximum of Tx. So Tx means the daily maxima, Tn means the daily minima. So the Txx means the annual maxima of daily maxima, Tnx means the annual maxima of daily minima, and so on. Similarly, we have the annual minima of the daily maxima and annual minima of the daily minima also. Similarly, they have this is for temperature. Similarly, for precipitation, they have the annual maxima. They have the maxima of the consecutive 5-day average. They have the maximum length of dry spell, wet spell, etc. So at any given location, they may have this kind of a GEV distribution, which includes the GEV parameters like the location, shape, and scale. So as you can see, IT means I may mean a particular location and T may mean a particular time, and also these mu IT, that is so basically what they are going to do is, they for these different parameters, they are trying to put something like a spatial structure on it. So if you consider this mu IT, that is expressed in this way, that is they have some basis functions xit, and the mu at any given given location and time is basically a linear combination of these different basis functions. Now the coefficients of this linear combination, they may vary from location to location, which we need to estimate. Or these basis spline functions, we may like some standard values might be used, or if necessary we may want to estimate these or the basis functions themselves from data, which will of course be more difficult. Now this so we have the y's, so we can actually transform the y to z by doing some kind of transformation, so that the distribution of z that is so basically this is the transformation which I talked about. And then like we can have this kind of a joint distribution in terms of the z's instead of in terms of the y, so like somewhat something like this. And they like of course assuming the like so there are n different locations, so that the time for the time being let us drop or let us just assume that this is like either it is like completely time independent or like it's constant over time. So let's drop the t for the time being and focus only on the locations. So like there are n locations at which we have these measurements, and so we have the z variables which we consider them to be independent, and we write it in this way. So they are, but they are, the observations are independent, but the parameters are not. So like what is necessary is to somehow like estimate these parameters. So for that purpose what they do is they divide the region into similar clusters, and all locations in each cluster may have the similar parameters. That is it. So basically they define something like a clustering problem, and the cluster variables is defined in using these I mean so they introduce these cluster variables C1, C2 up to Cn. So each of the locations, they are associated with this C variable, which indicates which cluster it is a part of. So so these cluster variables, they can take for any configuration, any cluster configuration, like this indicate this is the probability of it. So like C1 equal to 1, C2 equal to 1, C2 equal C3 equal to 2, this is one configuration. Then C1 equal to 1, C2 equal to 2, C3 equal to 2, this is another configuration. Then C1 equal to 1, C2 equal to 1, C3 equal to 1, this is another configuration, and so on. So each of these cluster configurations, each of them will have some kind of a probability, and that is specified by what is known as the Potts model here. And then like so based on that they can determine the strength of the spatial dependence also, like using this d of phi. So so like basically what they need to do is they need some kind of a conditional dependence, because we do not know these all the cluster variables. So they like we need to estimate each of them. Basically we need to do something like a clustering. So what they do is the clustering is done not by a deterministic approach like k-means, but by a probabilistic method. So for every variable, that is we try to estimate its its cluster coefficient conditioned on the cluster assignments of the like other locations, and that is done using like this. So for that we have a probability distribution like this. So we can say that this is something like a prior distribution on the cluster of every location. So then basically when we have the observation zit, so like we can it follows the GEV distribution according to the parameters like this, where the parameters are like they follow like each of the parameters are like they are dependent provided they are all in the same cluster. That is like all let us say the cluster, the cth cluster. So for all the locations within the cluster, the this z value, they follow one particular distribution. So they have so we can come up with this kind of a joint distribution, and it can be shown that if this is the case, in that case the actual distribution yi, which is actually what we observe, the maximum values that we observe before all these transformations and so on, it follows a GEV distribution what it is expected to follow. So then what is required is like we need, of course what we need is now to estimate the parameters as well as the latent variables like C, the clusters. So for that we have to create something like a posterior distribution on the clusters. So, like earlier we had a prior distribution on the cluster variable. Now we have a posterior observation on each of the clustering variable based on not only the other clusters, but also the observations y or z, whatever you call it. So, this is that posterior distribution. And so, like, and apart from that, for these transformation matrices B, A, etc., like which were like used to define these the parameters of the GEV in any particular location. So, these also have to be estimated based on the data and all the clusters. So, so we do something like Gibbs sampling, where these different sets of random variables. So, A, B, C, these are the latent random variables, and then those alpha, sigma, etc., those are the different parameters. So, we do the Gibbs sampling here to that is in the way which we have discussed in another lecture, to estimate all those. And once we have all the parameters, then we can like at any given location we can that is like we can plot the location, shape, scale, etc., parameters of the GEV distribution. So, here they have created a map of the different GEV parameters like this. So, like for the scale, they have, this is the map of the scale parameters of the GEV. You can see a reasonably smooth variation over space. This is the map for the location parameter of the GEV. Again, you can see some smooth variation over shape and so on. It will be interesting to see what are the locations which what are the regional clusters which they have obtained. So, for example, this might be one regional cluster, this might be another regional cluster, this might be a third regional cluster, and so on and so forth. So, these are the references of the papers which we discussed today. So, the key points to be taken home from this lecture are: first of all, the Bayesian probabilistic and probabilistic analysis are very suitable for understanding these extreme events. The dynamics of the latent state variable can be expressed as a stochastic model, and the parameters of these background distributions, they themselves have some special properties which can be expressed through suitable special priors, as was discussed like here, like this by this kind of a like regionalization analysis. So, that brings us to the end of this lecture. We will, in the following lectures, we will see a few more use cases of machine learning to unearth more insights of the earth system processes. So, till then, bye bye.